got loyalty, got royalty inside my DNA.
Sure. So the title has changed. Everything is ready. We'll start with a gentle introduction of what PL Talk is. So, hello everyone. Welcome to PL Talk. This is a weekly live stream by Hongi and me. It started when Hongi and I decided to stream a discussion of a paper once as an experimental thing. And then now we're stuck forever streaming for the rest of our lives.
Do you want to like complete your introduction of yourself, Jean?
Yeah. So I'm Jean. I previously was an academic working in programming languages. I'm now the founder and CEO of a company called Akita Software, like the dog, and we make API tools. So we make tools specifically to do observability, but like in an API centric way. We tell you all about your APIs. And we actually started out building a fuzzer. That's really how I got to know Ned. But when I introduced Ned, I'll say more. Hongi can go ahead and introduce himself more.
Hey, I'm Hongi. I work in security at Figma.
And our special guest today is Ned Williamson. So Ned works on Google Zero. Ned is, I described him last time as a fuzzer. Ned fuzzes a lot of things. He is a world expert on using fuzzing to do exploits. So if you Google Ned Williamson security, you'll find some of his high profile exploits. I feel like one of his exploits is even known as Ned Williamson's exploit, which seems like a big deal in the security world.
That's funny. I know that.
I emailed you this once. I was like, Ned, there's a whole article about your exploits. I found it. But yeah, Ned is really enthusiastic about fuzzing. It seems to be Ned's tool of choice. And so today he'll talk to us all about like, what does it look like to do fuzzing from the offensive point of view, like as a consumer of these fuzzing tools for this purpose, what does it look like? He'll do a really cool demo, and he'll also show off a very cool sweatshirt he's wearing.
Yeah.
So this will all come soon. We don't know when this will happen, but at some point on the stream, we'll see. But yeah, Ned, do you want to just give like a quick intro of yourself, how you got into this, and what you do now?
Sure. My name's Ned. I'm currently a security researcher at Google Project Zero, where I do vulnerability research. But I've been basically doing vulnerability research for probably something like 5 years now. I can't believe it's that long, but you know, maybe short depending how you think about it. But I guess, yeah, I guess my background is that I always thought programming languages and program analysis are just a really interesting topic, like this idea about finding bugs automatically, or like the relationship between different programming languages and the kind of bugs that occur or like could be prevented. Just the kind of the whole space of programs and bugs is interesting. So I also had this like long-term like childhood interest in things related to hacking, and I kind of knew about this idea of exploitation. And I think in high school I saw a documentary about Stuxnet, which I think they had just discovered at the time, you know, which was like this, all these zero-day vulnerabilities were used by a nation state to, you know, for an operation. Like you can look it up. But I just remember thinking like, oh my gosh, I can't believe this exists. There's a thing where people are finding unknown bugs in Windows that are worth like huge amounts of money. And it's like this huge kind of secret industry that kind of pops into the public eye sometimes. And to me, somehow that just seemed like the coolest thing ever. So somehow those things are actually pretty related, you know, like bugs and exploits are linked. So that's kind of how I ended up with fuzzing. Was, you know, the one place where those kind of overlap. Yeah, you can read the comments for more detail on that. I don't want to say anything. I don't know too much about Stuxnet. Yeah, it was something in Iran, but Yeah, it's a basic overview of me.
So something that I first met Ned when I was just talking with security engineers about like their process, and something that really
Hmm.
struck me about Ned was like you have a really like good description. You have like both a really good process and like a really
Hmm.
clear way of communicating it. So can you just talk about like what is your job and like what what's like the arc, the narrative arc of
Yeah,
finding an exploit?
sure. I mean, there's kind of like two angles to this. One is like what I do now, and one is, I guess, how I got to it through the process, which is probably interesting. Yeah, so I do think like there's a big image of, well, okay, I should first say what I do, which is to find security bugs, generally memory corruption bugs in really important, you know, software. So uh, there's a type of security research where you look at things like the Chrome web browser, or an operating system like Linux or Windows, the kernel, or just really anything where there's like um, a huge user base who kind of relies on those components being safe. So if you go beyond phishing, uh, and say, well, if I click on a link in my browser, I should never be compromised. Uh, there's a set of bugs that exist, that kind of are always exist, unfortunately, that permit you to do an exploit and have this kind of capability. And so I think that's this problem that I work on, is like, how do you find these really impactful and difficult to find bugs? Um, and how I got to fuzzing was actually kind of roundabout. So I started off thinking, like, kind of naively when I was in school, that like in university, that, oh, there's going to be some breakthrough thing that we're going to find, or that I want to participate in finding, that will kind of solve this problem, like automatically discover all these bugs, like kind of change the whole industry or something. And I didn't know what that was going to be, but I was, without having any practical experience, I was guessing that it would look something like that. And then I kind of quickly became disillusioned, because it seemed like all the people who were finding these important bugs were like these geniuses who were kind of hard to understand what the process was. There's all this like mythology around them, and no one was really using that much automation, at least publicly. I mean, people have always been fuzzing, but um, it seemed like a lot of the really respected and big research was all done manually. And so I thought, well, I don't care. Like, if I'm going to automate anything, I have to know how to do it first. So I might as well practice on my own. Um, so the kernel KFC, I shouldn't read these. I'm going to get distracted. You have to moderate for me. Um, but yeah, so I realized, I want to learn how to find these bugs manually, and I spent a lot of time on that. That's when I worked on this Nintendo 3DS project, where I tried to exploit the console, and I did it all manually, and it took like hundreds and hundreds of hours. And I just realized, like, okay, I kind of see how to do this, but this is so painful and time consuming that I don't think I could sustain this. Um, but by that point, I kind of knew what I was doing enough to start to be able to like automate some aspects of what I was doing. So I kind of went back and looked at, like, what bugs are people finding, and how, like, could we have possibly automated a way to detect these? And I just started to notice that fuzzing seemed like, as a tool, is really well understood to be useful. But I kind of saw how a lot of bugs seemed discoverable with fuzzing, that without knowing what the bug is or exactly where it is, it seems really plausible that you could make some pretty simple, or there'd be some pretty easy hypotheses you could test with fuzzing that would reproduce some of the bugs that people were finding by hand. And so I just kind of pursued that. And then, I built this system where I basically just I would look at like every bug report in Chrome for like several years and try to understand like how could this have been discovered? How could I plausibly have thought of this without knowing what it was? And pretty soon I kind of figured out the pattern, and from there became pretty productive with finding bugs in Chrome and some other places. So yeah, ultimately it started from like extreme skepticism, and then it ended up being what I kind of expected, which is that I think automation is actually really effective. So and fuzzing is really easy to understand, I think. So yeah, that's kind of the overview.
How do you typically select the targets that you're interested in fuzzing? I mean, imagine with certain things like Chrome, you have some instinct on which parts of the attack surface are like particularly interesting or might be particularly prone to bugs. But I was curious if there are other factors that go into you like sort of looking at what you tend to focus on, or what.
Yeah, I mean that's where a lot of like the security related skills come in, and that part is a lot less related to bug finding in a raw sense. Like those are kind of just orthogonal things. And I think that really, it kind of comes down to experience, and also there like basically you kind of just think about like, well, what's important to people? Well, like Chrome being security is important to people, and what about it is important? You have a sandbox that you shouldn't be able to escape. So then you look at like, well, what is the sandbox? What at a high level, it's like there's an attacker who has some capability to do something, and there's some system running somewhere that accepts inputs from the attacker, and then so you just kind of narrow down. You think about like as you zoom in, you start to have to use more of your intuition, like just from looking at different components. Certain things look generally, the more complicated components are, the more likely they are to have bugs.
Yeah, they have bad code smell.
Yeah, exactly. But it goes a little beyond that. Like part of it too is also understanding the community, like what people have been researching. So even if something looks really bad, if it's had a lot of review, it may actually be okay. But yeah, it's nothing too brilliant, really. It's just like a lot of experience. I think you just kind of build up an intuition. Yeah.
Cool. Now, do you want to just jump into the demo? There are a bunch of questions
sure.
in the chat, but I'll try to figure out like when to ask them as you're going through the demo, just to make sure we have time, because I know you put a lot of work into preparing.
No problem. Yeah, I mean, we have plenty of time for it. It's not too long of a demo actually, because it's kind of pre-baked, like a cooking show, but but I do want to make sure that whatever I do cover here, like that it's not too, so part of my assumption here is that you had a fuzzing talk before with John Reger, I think, and so I wanted to kind of add more of a specific demo of it. But if people don't know what it is in this call, like it might be useful to give some of the essentials, or maybe I can just cover that while I'm demoing.
Yeah, I think if you want to say like a couple of sentences about like, what it is you're going to show, like how that fits in the context of other similar tools.
Sure. Yeah. So I guess I might as well just start showing the code, and then I'll just talk through it. Okay. So hopefully this is visible. Let me know if it doesn't look right. So what I've done here is I've created a fake little addition to Chrome. And the idea is it's kind of based on work I did in the past on the Chrome sandbox. And I don't think this is actually true today, but at the time, anything involving networking was outside the sandbox. So if you found a vulnerability in any thing networking related, this would have been a critical security issue. So basically, I've created this kind of fun little class. Let's say this is like, well, I'll just describe what it is, and I'll talk about what fuzzing is and how we're going to do it. But the idea here is we have an API that we can access from a renderer. So let's say, I don't know how much people know, but like Chrome has, multi-process architecture where most of the rendering and kind of code that's harder to write safely is all sandboxed into like each tab essentially. And then there's one browser process that lives outside the sandbox that like orchestrates everything. And so the renderer can talk to this browser process, this like privileged process. And this is no different from saying like, an unprivileged process talking to some other privileged process or to the kernel or anywhere. Just kind of a fundamental security boundary here. So in Chrome, we have a lot of things that look like this, where there's some API that's exposed. There's quite a number of them. And so if we can send inputs to this privileged process that trigger a memory corruption, we can likely write an exploit and take over that process or run code in the context of that privileged process. So here I just wrote something really simple. So I just created this like fake header jar class. I think there's actually something called a cookie jar in Chrome, which I think I used in an exploit before. So it's pretty real. And so I came up with this kind of funny idea about like signed and legacy headers. So like, let's say we're trying to come up with some new like web standard with signed headers, just to make it a little interesting. But ultimately, if you're a renderer, you can say, hey, I have some response headers I want you to track for me. Print headers, you probably wouldn't see this actually in Chrome, but you'd have something like maybe log something or fetch something. And then I came up with this third API called merge headers, which you could say like, oh, if you have more than one header jar, merge them together. It's just something silly. You wouldn't actually be able to send a pointer if this was real. You'd probably send like an ID, like a file descriptor, but just for simplicity, I just left it like this. So the question is here, we look at this code, we see it's kind of non-trivial. The important stuff is, there's basically these few functions. So we have something that's ingesting these headers. So we parse out all the header lines and we go through them, enumerate them into a map. And then we then process these pairs by adding them to our like database. And when we're adding these headers, we have something that checks for some signature. And there's some logic here about, what do we do when we're merging together? What do we do if something looks signed or unsigned? So again, this is all completely made up, but it has the kind of the structure of what you would see in a real code base. So then the question is like, well, what is fuzzing and what do we want to do here? Well, the idea is, yeah.
There's also a question, sorry, earlier in the chat, like what languages do you fuzz? Maybe you can also give some context of like what things you have fuzzed before, because I know you've told me before, like, well, I've been fuzzing this, but I'm going to move on to this next.
Right. Yeah. So that is a really important thing, which that's why I was thinking we may even have to discuss some of these broader topics before the demo, because fuzzing itself is just a randomized testing approach. So it's just randomized testing. And so that could really be used anywhere. But in the vulnerability research world, we also have this huge problem with memory unsafety. I mean, everyone deals with this, but in particular, because there's a security impact to memory unsafety, it's a big part of what we deal with in vulnerability research. And so mostly this boils down to finding memory corruption bugs in C or C++ code bases, and then writing exploits for those bugs, which is kind of like its own little skill set, which is a bit orthogonal. But you can, in theory, fuzz any language, and there is value to fuzzing any language. Really, fuzzing, I think, is just a dynamic testing strategy that lets you check for properties about what you're testing at runtime, which you probably realize there's this thing called property-based testing. It's like an old idea that actually came from, I think, Haskell, the Haskell community. So a lot of these ideas were actually kind of generated, I think, or overlap a lot with like programming languages research, and just happen to apply to practical vulnerability research as well. But we can go more into my opinions on like different language and things like that later, but hopefully that makes sense.
Mm-hmm.
There's a quick follow-up question, which is like when you're doing for like the fuzzing tools you use, I guess we can focus on that. Like, did
Sure.
they help you shrink the bug for repro? Like, what's the relationship between like the fuzzers and the reproductions?
Yeah, absolutely. So that's a big part of it. And I can try to demo that actually in this example. It's not necessarily, unfortunately, the way I set up my example, it's not like going to be a completely readable test case, but we could still see that minimization is possible. But just since we're on the topic, essentially how that works is whatever fuzzing you do to get to an input that crashes, you kind of flip things around. So initially you start out running the thing repeatedly and you never see a crash and you're trying to explore till you find a crash. And then once you have a known crash, you just keep rerunning, and then you have this invariant that it still crashes. So you just flip the scenario. So now you keep rerunning and trying to just randomly shrink the input and fuzz it. And whenever you see it shrink and still crash, then you iterate, you recurse on that example. Of course, like anything else, this is like a massive, it's a very generic problem that you could solve in many ways. And it's just like, if you have a fuzzer already, you might as well just reuse the infrastructure to shrink, and it works well enough to be useful. But most of the fuzzing tools today have that built in, so I can definitely show that. Yeah, was there anything else to start with? No? Okay. Yeah, feel free to interrupt me if anything else comes up, if people are curious. But so the basic problem we have here is there's no, I think if anyone's familiar with fuzzing, it's basically like, most people probably have heard of this idea of like you have some JPEG parser that you feed bytes into some parser and try to make it crash or find some out of bounds access or something. And a lot of work has gone into testing these kind of libraries, but most code with security relevance actually doesn't have that format. Like, it mostly is kind of glue code or has these complex APIs like I'm showing here. And so we need something that can test everything about this in a generic way. And there's kind of like too much to cover here for the time, but there's two parts to this. One part is like how the fuzzer guesses and what it's doing. And then there's like, how do you hook up the fuzzer to the thing that you want to test? So I'll be showing the latter thing, but the former thing I can kind of mention as we go through it. Now, basically, what this boils down to is, if you think about how you would test this with a unit test, you would write some C++ code that would call these functions with some data that you know about in advance and make some assertions about the state of the system or some expected output. So the difference with fuzzing is we can't easily, unless we have some simple model that we're comparing with, we have to have some property that we check dynamically. But the nice thing about looking for memory corruption bugs is we have tools like one called address sanitizer. Or even if you don't have that, you may see a seg fault when there's a corruption. So we have a way to essentially dynamically check for errors already. So all we have to do is find a way to just interact with this in a generic way. So whereas with a unit test, you would be asserting things. We essentially write something that looks like a unit test, but it's random, and we just don't assert anything because we could if we want to, but if we're looking for memory corruption, there's nothing to assert. We just hope it doesn't crash. Or another way to look at it is that actually assertions are being checked every time there's a memory access by the bug detection tools. So just to save time, and because demos are hard and error prone, I pre-wrote like the main part of this. So this is like, there's this simple data structure called fuzz data provider that's actually now part of LLVM by default. And I'll be using LLVM's fuzzing tools here. And so what this LLVM fuzzing infrastructure asks us to do is to just provide a sequence of bytes and do something with them. And it will worry about what to feed here based on some compiler instrumentation, or using feedback from running it with compiler instrumentation. It will basically guess what to send to it, and it will learn over time, which we can talk about. But the main thing here is that I use this helper class called fuzz data provider, which just wraps the data that comes in and gives us some convenience functions. So we can just consume this random string of bytes as a stream and say, what do we do with this sequence of bytes to kind of translate it into an interaction with this HTTP handler header jar thing. So just from looking at this, well, we know that we want to call all these functions, and then this one's a little tricky because we want to be merging two jars together. So there's a number of ways you could do this. You could randomly create some number of jars or something. Did you have a question, Jean, or?
Yeah, I was thinking it might be good to zoom out and talk about what the fuzzer is going to do, like what we're setting it up for.
Yeah, this is the challenge because it's so it's a pretty packed demo, I guess. But what the fuzzer is going to do is take these, as I said, it's going to feed something here, and this function runs and it returns, and it will just keep calling it with random inputs. And people who are really familiar with fuzzing may already know this, but a kind of big breakthrough came in 2014 with the creation of AFL, which is a fuzzer that basically kind of built on some intuition that was already there in the community. But what it essentially demonstrated was that if you have your compiler instrument feedback for code coverage for the code that you're fuzzing or testing, and then you feed inputs randomly in, and every time you run it, you check the coverage that was achieved by the input, you can actually use, I think, like an evolutionary algorithm to essentially find better and better random guesses. So starting with some corpus of inputs that gets fed into this, or from no corpus of inputs, you have this process that essentially picks a random known input, mutates it slightly and runs it. And then you look at a bunch of metrics like, did we cover something new? Or did we actually make this test case shorter and it has the same coverage? Or did something improve about this test case compared to our old one? And so we either replace the existing test case or we just add a new test case. So over time, you have this corpus of random inputs that is growing and kind of constantly becoming more efficient as we do random testing. So we have kind of this function, like given the current set of random input guesses that we have in our corpus, they map to some amount of coverage, some amount of time spent, some amount of space or some amount of data size. And we just keep doing random trials trying to improve on these metrics. And it just turns out that this works extremely well. It seems like it's sort of like most of these kind of like almost untractable problems is that when you have a randomized algorithm, you can kind of get through most examples really cheaply. So even if we can't prove things with fuzzing, we can still find a lot of bugs in the process. And so, and that's the truth of code bases today, is that even really security critical code bases, because we have so few tools to prove anything, we barely even test or try at all. And then so there's just all this low hanging fruit that's sitting around almost everywhere. And this demo is trying to kind of be an example of that. Like this is, I think, a somewhat plausible piece of code. And funnily enough, like, I mean, just looking at this, I like this example that I came up with here because it's not clear where the bug is. Like just looking at this, I don't think I could tell you. And if I gave this to anyone who's a security researcher, they could probably find it. But when you're talking about millions of lines of code, you don't know that there's something here. It takes a lot of work to find an issue. And what's funny is this is actually more complicated than reality. So the first Chrome bug I ever found was just if you created a database with a given ID twice in a row, you have a use after free vulnerability that lets you escape the sandbox. And it's worth $10,000, $20,000, maybe X amount of money in the black market. And it was literally because they just didn't have a test case that creates a DB twice with the same number as an ID. So this is the problem that we're trying to address here, is like, how do we test huge amounts of code and just get some coverage over it so we find issues that are being neglected. So sorry if that was a little ranty. I don't know if that
no, that was
helps,
good. There's a
but
follow-up question, which is
sure.
like, how does coverage information feed back into the fuzzer? And so there are some people in the audience answered, but I feel like there's also like a higher level question to maybe address, which is like, like, is it always automated, or like, do humans use that coverage information sometimes and do stuff with it?
Oh, absolutely. That's what this demo is really about, is what the tool is good at and what I do. I'm trying to kind of show what I bring to it. Like, what does it mean to be an expert fuzzing person? Because that almost sounds like silly, if you think about what fuzzing is. Like, what am I doing? Well, I am doing something, and it mostly is also simple, but it's not completely trivial. So it's kind of what I wanted to show with this. Do you think the question was sufficiently answered by the other people in the
yeah, maybe we can like
or...
continue with the demo, and then like people can ask
Sure.
more questions if they still feel confused.
Yeah, I think there's a lot involved in that topic of like, what approaches can you use to better and more intelligently mutate the test cases, because I think there's a lot of...
Oh yeah, I mean, it's a whole research topic that is like totally immature. So but in any case, I guess hopefully this is not too complicated to follow if you haven't seen this. I'm sure basically no one has seen this fuzz data provider class before, but the idea is that it's a way that lets us interact with this random data that's coming in. It's essentially an extremely simple parser that we're creating here for some made up format that interacts with the interface that we care about. So just going back to this, I mentioned like we just kind of want to do something simple here. There's a lot of creativity you could have here. Like we could create a bunch of header jars, do things with them, merge them all together. But just to get started, I tend to do the minimal thing, which is actually enough for this issue. And so I just thought, well, I'll create 2 header jars, and then I'll loop through my input while there's some data remaining in the input string. I will pick a random number, basically consume a byte from the front, and use modulus for something. You get a number between 0 and 2 inclusive. And we just switch on the different API calls that we can make on the header jar. So cases 1 and 2 down here are really simple. In one case, we just print the headers, like we just call the function, and here we just decide, well, we'll always merge from 2 into 1. And then we just have this thing where we consume some random amount of bytes. We guess a number, we consume some string of bytes from the input, and then we flip a coin, consume a Boolean, and pick which header jar to feed some bytes into. So the main important thing here is like that if you think about what the attack surface really is, it's some sequence of API calls that the attacker can call this. Maybe it can call API calls in any order arbitrarily with any data. And that's the thing that I want to preserve to let the Fuzzer Explorer for me. So if we go ahead and run this is what this is going to look like. Okay, so there's some setup to actually connect the fuzzer to this that's part of Chrome that I didn't show, but it's essentially some like build flags. And if you were doing this at home against something completely new, it just boils down to some LLVM flags, some sanitizer flags will link in all the fuzzer stuff for you.
Do you mind
but in any case,
zooming
sure.
in a little bit? I think it might be a little small for the audience. Cool.
Yeah, this one is definitely too small.
Yeah. And also, I just had a quick question. Is
Sure.
the fuzzer in LLVM, is it based on AFL or does it use AFL under the hood?
It doesn't use it under the hood, but it's quite similar. It's essentially the same design, just built into LLVM, and that's sort of helpful because there's this is probably distracting. People won't listen, but the compiler instrumentation is part of it. So to have that implementation be like synced with the runtime component of the fuzzer is helpful. And AFL also forks every time it runs a test case, whereas libfuzzer runs in process and just calls the same function repeatedly. So that's better suited to my workflow, which is I want more performance and more manual intervention is acceptable to me. So don't need forking. So what we see here is, okay, we're running the fuzzer, and I can talk about some of the output. So we're running about 1,500 test cases per second using 500 megabytes of RAM. That's pretty reasonable. It's testing random sequences of up to 895 bytes. And currently it says that our corpus is size 816 test cases with 91 kilobytes total. And probably the most important part here is the code coverage. So I think this represents essentially like number of lines covered. It's a little bit abstract because it's not that simple in the compiler's perspective, but you can see that from when we started, I already had some corpus from when I was testing before. We could just remove it and rerun it. So if I recreate the corpus directory, we're starting from scratch here. There's no test cases yet. And then we'll see how it does. All right, so you can see that in the beginning, there's basically no coverage. And it's quickly, basically anything it does is gonna find some new coverage. And so we've gone through, I'll just stop it randomly. So now we've gone through like 70,000 random tests. And at this point we have 3,700 units of coverage and corpus of size 500. So you can see that there's a pretty big disparity here. So we have a pretty small corpus relative to the number of runs that we've done. And you can see it basically starts out small, like with 63, 53, 58 bytes, and it wants to see how much it can get away with small inputs, and it like slowly grows as it gets harder to find more. So I'll run this for a little bit, and then we'll see that we'll get a bunch of coverage. And I think a lot of people might say like, okay, we run this for like you'll see people do things like this, and I think then they'll set it up and say like, oh, let's run this for a month and then come back and see if we found bugs. But my approach is to be extremely manually involved here. So at some point, this might trail off or whatever, but I just want to dive in right away and see what's happening. So even at an early stage, we can look at that. So but maybe also zoom this in. This part doesn't matter if people read it, but essentially I have this second build of the fuzz target with a different kind of coverage instrumentation. So in this case, it's not it's not machine code coverage meant to be ingested by a fuzzing framework. It's code coverage that's meant to help you visualize the current coverage. So it actually maps like line numbers to all the coverage that we see when we run it. So almost everyone in the audience probably has used something like this at some point. This is actually something that was developed, I think, for unit testing, where you just have some code coverage report to show how your unit tests are doing. So you didn't see anything, but I ran this thing here that essentially runs the fuzzer. Oh, actually, I kind of messed this up. So I want to run this over all of the current corpus and then collect. So yeah, you can see there's a lib fuzzer build and a coverage build. So there's the corpus. So yeah, sorry, I have to rerun this. But what I'm going to do is I'm going to run this over our existing corpus folder with all our entries, and then just dump out this HTML report that we can look at. Yeah, unfortunately with demos, it's kind of slow, but I'll pull this up in advance and we can refresh it.
Cool. So there's some questions.
Mm-hmm.
So one person asked, are you just directly linking to the fuzzer to the code and just having it run over that?
Yes, exactly. So that's why this function is not main. So there's a fuzzer. The fuzzer is like a runtime library that has a main function, and it links against your code, and it just expects you to provide this API somewhere in your library.
Okay, cool.
Yeah.
And then somebody else noted that there's actually quite a bit of manual work in thinking. And so like they were wondering if you had thoughts about how to automate that, or, is that why you still have a job?
Well, right. Yeah, it's both. It's both. So I think the interesting thing is like this essential concept of like looping and doing different API calls is a format that I've just been using for a long time. And it's the part I'm about to show you that's actually kind of the secret sauce, but I think a lot of this here is really rote and can be automated. Essentially involves, it's sort of like, could you automate writing unit tests? It's kind of a tricky question. It's like, you kind of can, but maybe it's also okay if developers just minimally understand what their API is and how to call into it. But for sure, this is kind of an obscure thing that not many people are informed of, even though the tooling is there, but it's pretty simple and maybe just needs to be made more accessible or just better advertised. Mm-hmm. So if we go here, I guess this isn't working. I don't know. Oh, I see. No, it is working. It's just my and here. It doesn't like that. It doesn't like it. But this should work. It just thought it errored because it didn't find any code coverage that the fuzzer is expecting, but really it did find it. It just, yeah, there we go. So this is what I typically use. So if we go through this, we'll see like, okay, where's our coverage looking good and bad in this API. So
could you explain like what is the, so I see that we're looking at the code, but like what's being highlighted? Is that what code paths are being covered?
Sure. So this is showing for this file, we have the line number, the count, and just the source. So this count shows how many times we actually executed the line. Mm-hmm. And so if we go back down here, it's going to highlight for us in red places that weren't covered. And this is the benefit of having this like human readable pass, like coverage pass. So even though the fuzzer kind of already knows this information, we just do a separate build so that we can get character level information about what's covered. Just in the past, I used to do them together in one build, and it was just kind of a mess. This is a lot nicer. But we see that we're missing some code here, and it will turn out, spoiler, that is relevant to finding a bug. So what are we missing? Well, one of the first things here is this check signature. Well, the fuzzer is going to really have a really hard time finding a way to give a string that we can split up here and then correctly have a SHA-1 hash. But as an attacker, I'm looking at this and I think, oh, I don't care about computing a SHA hash. Like I can just do that manually in a millisecond. It's just going to be hard for a fuzzer to guess this at scale and fix that. And this is something that like every fuzzing demo kind of covers. This is the simple part of this demo, depending on what you think. But essentially, we can just comment this out, or we can. What I do is I actually snuck this in here earlier. I expose this fuzzed data stream to my library that I'm testing. And so it seems kind of weird, but this is something I actually do fairly often. So if there's some check that I know is a bit hard to pass for a fuzzer, but I know logically I can pass this check by hand, then I can do something like this. Like if this global fuzz data stream, if we consume a bool, we can decide to return false, otherwise continue and pretend that this worked fine and we don't have to pass the check. So a bit weird, but this is like something that I do fairly often. You'd be really surprised how well that works. So if we run this now with this like expensive check commented out, then yeah, sorry, I'm running this on my laptop, which is part of the COVID experience here. So it's not that fast, but just let this build. It's funny, but actually all the research I ever did as an independent person, I just did on a really old MacBook. So this isn't even that unrealistic, but did you have a question or comment, Jean?
Yeah, someone asked, is the coverage active only for the code you wrote? Like, how's the coverage work?
Yeah, the coverage is active for everything that's built into the binary. So if I go back, I don't know if this works. Yeah. If I go back, you can actually see like basically everything in the code base is here. So we could look anywhere. It's a bit laggy, unfortunately, because of my laptop being slow, but you can even see like some third-party libraries like time.cc, whatever. Like this, in theory, is all some utility code here we can see was covered. So in theory, we could look anywhere. We're just focusing on this part because we're scoping the fuzzer that we're writing. So now I commented that checkout, so we would expect to see that we can pass the check. So I'll rebuild the coverage. I'm realizing this is taking way longer than I expected. So we're almost to the end, but I just think like my other demos I won't have time for. Like hopefully it's okay if we go on longer. I'm happy to chat, but.
While we're waiting, just like a quick question for me. I was curious, because I've also seen some like protocol aware fuzzing approaches as well. Do you ever try some of that when you're, because I see like here's one technique you just showed for, well, I don't really want to deal with this check, and it's, I can see it's not really relevant for my fuzzing, so I can just, replace it. And then I imagine there are other times where you might actually you might care about like certain message formats and things like that.
Oh, completely. Yeah. So everything I do here, so what I'm trying to show is like shortcuts, because I don't know whether there's bugs here or not. So I want to test and get a feel for like, what's the quality of this code, or like, is there maybe bugs that are hidden? And so And if I wanted to be totally sound, I could easily do that. I could go here, and instead of just passing raw bytes in, I can consume this input and say, okay, consume a string for the name, consume a string for the value. And then I actually construct like the SHA, put it in and call the function. Like that all still works. This is just like a time saving thing that I do. But yeah, it is one of these things where like the significance of this slight difference is like nothing to people who care about programming languages and theory and stuff. But to people who are like, well, how is it that you find bugs and these important bugs or whatever, like what is going on? This kind of thing is really critical, because you actually don't, you need a way to get some volume of things happening where you're finding something without spending too much time. So yeah, so anyways, so I ran this again. Don't worry about this. This stuff is just like when I'm printing the headers, which is just random garbage. But let's see. So if I rerun this, wow, my laptop is so slow. I need one of those new M1s.
Oh yeah, I got an M1. Now I can have like 300 tabs at once. That's like the
No, yeah.
Good for.
I'm on the old, yeah, my laptop, it has the keyboard that doesn't work and all that, but no M1. So just joking, no disrespect. But anyway, so if we look at the coverage now, apparently this didn't work, sadly. I don't know why. Sad demo things, but I'm pretty sure it works if I just completely disable it, so I can force it to work. That will get something. So yeah, again, sorry, this is it's like so kind of time consuming, but
yeah, no, John Regier actually refused to do a fuzzing demo because he said they're too hard. So I think it's very admirable that you're attempting it.
No, it is really hard. So I may like cheat a bit and jump ahead. So I know that, yeah, like normally I do things through SSH, not on my laptop. So it's not normally this slow, but I think the Mac OS, the file system is like a bit slow for the way that Fuzzing likes to use it compared to Linux is a problem here. But so, okay, now we're seeing some more coverage. Run it again.
Yeah, I think like demoing a random tester is like very unpredictable.
Yeah, it's pretty much, but there's going to be some modifications I can do that'll get it to like work instantly. I'm just trying to show like a somewhat natural process here.
Yeah.
But I'll cheat a little bit because we're so low on time and I want to make sure to answer questions. So I have this like thing that I snuck here. So the other half of this that will turn out to be slow is this is one line, but what it's actually doing is it's a full HTTP header parser that's taking this string, this raw string that we're passing in, and parses headers out of it. And then here we're looping through and creating this local data structure with the headers in it. So this is extremely representative of stuff I see where like, I don't actually care about fuzzing the HTTP parser because everyone has fuzzed this thing already, but it's kind of a prerequisite of getting to the real code here, which I want to test like the logic of this code. So what I would do is I'd actually say, don't even bother parsing this. Don't do this. I'm going to replace it with this code here. And sorry for jumping around. Let's see if I can get it quick. This might actually be broken now because I edited stuff, but yeah, this is kind of, oh, I think I see what's happening. So I think I was failing to actually even find test cases with a slash in them, which is funny. Yeah, this might be a disaster. I don't know. But just jumping ahead here, we would have realized that, this parsing stuff is really expensive and we barely get through it. And so what I'm going to do instead is say, don't parse anything. In fact, this is a bit wasteful now because we don't even touch this data. We should probably not be passing this data in anymore. But a thing that we can do is just pretend that we parse successfully and we force this code to work. So we just say, just populate some number between 0 and 4 entries into this dictionary. And then, so at this point, we're skipping the parsing, we're skipping the SHA checking. So almost everything boils down to like guessing where slashes, like having a slash somewhere in the input, and just calling these different functions with these different cases, which is like flipping a coin. So we've kind of taken the complexity out of the code base with like a few lightweight hacks and then turned it into something that fuzzing like doesn't have any problem exploring. So
someone asked,
we
would
run
the call in the for loop condition be called on every iteration?
Yeah, I suppose it would. You might want to extract this out. But let's say that's broken and run it anyways and see if it works. This is how bad we can be, you know, with fuzzing. It's so this time when we run it, I think. Oh, I see the problem. I think no, this is right. It's just demo bad luck. I don't know. I ran this like 100 times last night and it was like instantly working every time. But we'll just run this for a bit and see. Yeah, might as well try that while we're at it.
Is it just like the randomness causing it not to work as smoothly?
I think so. There's a lot of like this corpus also is, like I said, it's always improving like globally. So even when you kill it and rerun it, it's resuming essentially. So it may have been while I was playing with it that it was like there was a bunch of work hidden in like my previous attempts here. That said, this should work. So
I guess that's also a good demo of like what can happen during fuzzing.
Oh,
yeah.
I see a stack trace. Yay, stack trace.
So yeah, we did find it. I sadly it was a little bit contrived, but because I didn't show like writing this by hand. But you can actually see here though there was only 9,000 test cases we had to try from wherever we were before it hit this crash. So now we have this test case, just sort of opaque, but if we run that again, okay, we see that it reproduces. So we have this minimize crash thing we can pass. And so now it flips it around and it's rerunning the crashing input and trying to find shorter examples. And it just keeps iterating. And every time it finds something smaller, it restarts from there. And so as you can see, it's minimizing. We can stop at any point. I'll just say stop it here for time, but yeah.
Someone was asking, what is the role of the corpus?
So the role of a corpus is it contains a current set of best test cases that we have for exercising as much code as possible with as small of a corpus as possible. So if we go back to where I was doing the fuzzing, might have run off the screen by now. I could just try to run it again. But you can see, not if I have it spamming. I want to turn off standard out for a minute. You can see, even before we got to this crash, which we reproduced a new version of it, that here this is saying, okay, this is a new test case. So we had a corpus of 260 elements, and we found a test case that increased the coverage by 1 unit, probably like 1 line of code. We go down here, we see we didn't increase coverage, but we reduced an existing test case. So we found a test case that's even shorter than one we know about, where the global corpus still has the same coverage, and we can replace a bloated test case that we had before. So over time, as you keep running this corpus folder is constantly getting new entries that have new coverage, or it's shrinking existing ones. So the efficiency of the coverage for whatever code you're targeting in terms of space and time is like constantly improving. And so as many times as you want to run this, wherever you run it, you can share a corpus folder with someone. This is kind of like the global state artifact that gets stored as part of this genetic algorithm that's used in modern fuzzing.
Cool.
Yeah.
So
we're
reaching. Oh, sorry.
I was just gonna say, yeah. So yeah, we're out of time. We may not have time to go into all the bug and everything, but there was a use after free in here that was logically happening here when we're merging headers. It turns out that we forgot to check something and we have a use after free. This is very canonical, like Chrome bug. So yay,
cool.
Demo.
Yay, no, this is really cool. Yeah, and I think it also it showed off some of the randomness of the fuzzing process.
Yep, completely.
Yeah, no, I think fuzzing is super hard to demo, so it's really cool you put this together. So we're reaching the end of like the normal end of time, and so what usually happens at this point is we move over to the Discord and people can ask questions in the stream of the week. But since we just came off the end of the demo, I think there's
why don't we do
we can wrap up like what's that?
Yeah, just a little bit might be helpful for people.
Yeah, I think like just
watch
like
YouTube
we could unless wait, Hongi, do you have to go somewhere very quickly?
No, I have a few minutes. I can stick around.
Okay, cool. Okay. So I think Ned, you can say like some conclusions. I also think that people are really curious how this relates to like your like big fuzzing projects that you've done. So like, you know, can you talk us through like when you like found like one of these big exploits, like how like, what's the difference between this and that?
So I actually have it open. I can do it in maybe 5 seconds. We'll see.
Yeah,
so
let's try it.
This is the same thing I showed except on the iOS kernel. And same exact concept, just vastly more complicated. This is actually open source on the Project Zero GitHub. But essentially it's the same thing. So if we go down, you can see I'm actually using protobufs, which let me write a higher level grammar here, but I'm looping and doing random syscalls with random arguments, and same exact idea. Anything network related, I'm doing random syscalls, and there's a bunch of code to like initialize things. There's a lot of like setup complexity here, but the short explanation is it's the same thing. A kernel exposes syscalls as an API. You call random syscalls, random APIs, same thing. You find a bug and write an exploit. There's like a lot of security knowledge it takes to glue all of this together, but the concepts are really simple.
Could you walk us through like, I don't know, what went through your head to find like, you know, what was the time frame like what were some of the ahas like?
Yeah, so some quick maybe time frame things here were so picking the target was seeing some, like looking through this kernel source code and thinking, oh, networking looks like it could be complicated and potentially really important because it's remote. Maybe send a packet to someone and exploit them. That sounds scary. I also thought that people probably haven't fuzzed this code base with as much like an integration style, like testing everything together, how it all fits together in the way that I wanted to for this project. And I had seen some bug reports popping up where people were finding issues by hand. So I thought, okay, I'm pretty sure I could, whatever fuzzer I was planning to write could have found these issues. So I just was kind of inspired to write one for the kernel networking. And yeah, that's all I did was just tried to be thorough and look at these coverage reports, see where things would get blocked, do little hacks, or, you know, in some cases, I have some things like, oh, there's some IP6 header that I'm trying to generate that's well-formed. But essentially just a much more fleshed out version of what I demoed. And yeah, so I think from starting to finding some initial bugs was like a month of work or so, like full time. And then I think it was a bit complicated because I was working on this part-time, like 1 week per month, but I was also running this at scale in the background. So however that balances out, I don't know, but it was like a few more months, maybe 5-6 months total till I found an exploitable issue that was, affected iPhones. And then writing an exploit for that was about a week or two, so a lot faster. But yeah, but essentially that's the message is like, this is open source. As I said, you can look up on GitHub. We could like maybe share a link or something, but just doing this to a much larger degree and with a lot more time investment is kind of how you find issues on these huge code bases. Yeah.
Cool. And I
Hey,
think
Ned.
someone asked earlier.
Oh.
Oh, sorry. Go on, homie.
Oh yeah, so I had a question I've been meaning to ask for a while,
Mhm.
which is, do you have any advice for, or like, what do you typically do to triage the findings, especially when you're doing a lot of this fuzzing at scale? Like my experience has been when I've been played around with fuzzing, like, oh, I can get a lot of crashes, but how do I figure out which ones are interesting to look at? How do I figure out which ones might
Yeah.
be exploitable?
Well, so this just comes with the target selection here. So basically, I'm looking at the iOS kernel. So if it turns out that there's 500 bugs and I find 500 bugs in it, like I'm very pleased to, I could spend a day per bug and it's worth it. But if I'm finding a lot of crashes that look really low quality, that's a sign that I'm making too many assumptions about. So when I do these unsound modifications, like changing the code that I'm testing to get through something faster, sometimes I introduce bugs that weren't there. And there's all kinds of things that can pop up, but generally I would just say I don't really have a problem with that. Like if something is so buggy, it probably, it's not the challenge that I'm trying to deal with. As an attacker, it's like I'm trying to break out of really difficult things. So if some aspect of it is super easy, it's like, oh, the second I see that there's a lot of bugs, it's like, there's no problem. You can pick one and exploit it, or it probably means it's not that important if it's that bad. But
And
it's a bit of a different perspective. Yeah, but
yeah, no, I think that totally makes sense. And when you say like, you like will look at some crashes and figure out if it's low quality or not, like what are some of the things that you look for? Is it just like, this is the type of, like, this is a use after free, it's probably, it's maybe very likely to be exploitable versus.
Right, exactly. So, and honestly, like the answer to that is really just, you have to kind of have experience writing exploits, which I did have before I got into this by doing CTF competitions. So I already knew basically how to write memory corruption exploits. And from there, it's tricky because it's something like, it when you see it, like you can categorize, and if you're at scale and you're trying to prioritize things, like a use after free or out of bounds write is like absolutely scared and like a null dereference. But ultimately it's highly bug dependent, and you kind of just, if you don't ever write exploits, you don't know what that next step is. But if you write exploits, like, okay, here's the next step for me. And then you can just look at it and say like, oh, this is going to be really easy to proceed, or, oh, wow, there's some huge constraints on this that I have to accept or find a way to deal with to move through the normal workflow. So just very dependent on the bug. Yeah.
Well, what was the longest it's taken you to find a bug that you like were working on for a long time?
Yeah, the Chrome actually. So it took me, I think, 6 months of working almost daily to find my first bug in Chrome. And I had up to that point been doing things where, like, something on Nintendo, something on, and this was all before I worked at Google, by the way. So no, not endorsing hacking anything, but when I was in school, like when I was in college, I worked on, like, I did some stuff with Python with the interpreter, and then Nintendo, and then I did some kind of sequence of things. And each time it basically took me like a month or two to find an issue every time I kind of went up in difficulty. But then Chrome was like 6 months, and it was really painful and scary. But eventually I found something, and then basically as soon as I found it, something kind of clicked, and I was able to kind of be productive from there. So I haven't really had problems since then. But yeah, I say 6 months, like even for iOS, that was how long it took. It's pretty involved. Yeah.
Cool. And this is related to a question Double Twitch has been asking since the beginning, which is how did you get to do this stuff at Google?
By doing the bug bounty, honestly. So it's kind of funny because I actually didn't even get an interview with Google when I applied when I was coming out of college, and then I also failed an interview a different time. At a certain point, I thought, well, I can at least do the bounty. There's nothing you have to apply for, so I'm just going to try to find Chrome bugs, and and that actually was pretty nice because in a way I got to build my skills without the pressure of having to perform while already at work, if that makes sense. So I kind of just gave myself free rein, like as my hobby, I'm going to try to pursue this and turn this into my job. And eventually I had found enough issues in Chrome that I think I still had to go through the interview process and everything, but there was like enough resume there, and honestly I just was better by that point, that I was able to pass the interviews. But I would definitely recommend that people focus on the core skill that they want to do. So for me, this happens to be at Google, but for you it may be freelance, it may be somewhere else, and it's a personality thing maybe, but for me it was like, oh, I really enjoy this and this is super interesting to me, so I'm gonna get really good at this to the extent that I can and just find what place wants to employ me. And it's kind of an afterthought, like what that is. So I wouldn't focus too much on the specific company or anything.
How would you describe your core skill?
That's a great question. So honestly, I think it's I ask myself that question every day. Like, what is it that I actually know that other people don't know? Because I see people who are really smart all the time, and I just can't believe that I'm contributing anything. Like, I don't even know what it is that I'm doing sometimes. But I think really it's just this like integration of all the relevant skills that, I spent a long time doing CTF challenges to learn to write exploits. I spent a lot of time in school learning about programming language stuff, which we didn't cover too much, unfortunately, but spent a bunch of time learning fuzzing, a bunch of time reading previous bug reports. And so eventually I think I just like kind of know the whole stack when it comes to this skill set. And I think I also just questioned maybe some of the assumptions that I was seeing. And so it's funny that like, someone asked like, oh, shouldn't you have used this, like you kind of did the for loop wrong or something. In a way, I have this like naivete about what I do that makes me like kind of not see certain barriers that other people assume are there maybe. And so I just kind of do a lot of naive stuff, and it just seems to work. So I'm not really questioning it, but I do try to learn, but it's really hard for me to like answer, yeah. But yeah, core skill, just programming, C++, debugging, all this,
Are there any interesting like technologies or targets that you're thinking about looking at in the future, like fuzzing hardware, for example, or firmware, or maybe looking at things like WebAssembly?
Yeah, absolutely. So it's actually a perfect question because you kind of captured both angles that things are going. So as people move to languages like Rust, or we have new mitigations like memory tagging extension in ARM, which will let us check for some of these memory corruptions. And we don't have time to get into it, but there's some features coming out that will mitigate a lot of these problems, or may be able to mitigate them in practice. And so things are kind of going two directions, which one is like things like WebAssembly or V8, like interpreters, things that are written in, you could have a JavaScript interpreter written in Rust, but if it's outputting assembly, you get it to output the wrong code that's corrupt, then you can escape in a sense. So there's things like that. And then there's things like, firmware, hardware that is kind of under-researched. And so I actually am interested in that. Like, I think that's kind of the next easy thing to be doing once it gets really hard to find bugs like this in browsers and other places. But we'll have to see. It's like there's like a global community and there's like a meta in a sense. If you know about like gaming meta, it's like as certain things get fixed or made really hard, there's kind of this awkward feeling for a little bit, and then the community kind of realizes like, oh no, we can still do this thing, and then it just kind of goes back to how it was. So it's something that I think about a lot, but I also accept that like I'm part of the community, and it's a much bigger community than me, and so as a whole, we will together kind of figure out what the challenges are going to be. Yeah.
Cool. Well, this seems like a good place to end the streaming portion. I don't know if you have time to stick around in the Discord for a little bit, Ned, in case people have questions for you. I'll send you the link. But yeah, here, I'll put the Discord link in the chat for everybody. And then Ned, I'll make sure you have a copy of the link too. But yeah, thanks Ned for coming. This was yeah, it was super ambitious to like put together a fuzzing demo, and I think that was really, really cool. Also, like I think it showed off a few things that I really liked, which is like it's not just like one click. I think like the developer experience around fuzzing is going to be like a really interesting point of innovation in the future, but also like the fact that it's very random. I think this demo very nicely showed that.
Yeah, it's completely random. It's very much like Wild West. There's no real. It's a lot of randomness, as you'd expect. So, yeah. Thanks for having me, and like hopefully people thought it was helpful, and looking forward to the Discord. Yeah.
Yeah, people said good presentation, very interesting, great demo. But Ned, we promised people one more thing.
Yeah. Oh, right. I do have you couldn't really see it on camera, but I have my fuzzing themed hoodie. Where to go? Fuzzed out. Yeah, nice. I'm a big fashion enthusiast, so it's funny they started making like hoodies for us, you know, gremlins who never wore nice clothes before. But yeah, this was my COVID purchase.
You find that it helps you get in the right mindset for fuzzing?
It does. Yeah, it's kind of cliche. Like I don't know why I have this thing where I'm like, oh, I'm not like other people at work. I wear hoodies or something. And I realize like that's nonsense. Like that's what everybody does, you know, I don't know. But yeah, anyways.
Cool. Well, yeah, thank you so much, Ned, for coming on and preparing this whole John Regier had refused to demo, so thank you for attempting.
Yeah, hopefully it wasn't awful.
And yeah, we'll see you on the
All right, thanks. Bye, everybody.
Goodbye, everybody.
Peace to the world, let it rotate. Sex, money, murder, DNA.